Okay, we want to prove that if a function f is bounded and monotonically decreasing, then it is Riemann integratable. So the lower Riemann sum is the sum from 1 to n inf of f over xi minus 1 xi times delta xi, where a equals x0, which is less than x1, all the way up to xn, which is equal to b, and delta xi is equal to xi minus 1. So using that definition, this would equal the sum from I is 1 to n, and the inf would be the value at the end because it's monotonically decreasing. Likewise, S upper would equal, pretty much it's going to end up being the same thing, except we use the supremum, which would be the value near to the start because it's the value at the start of each interval because it's monotonically decreasing. So that's f of xi minus 1 delta xi. Now let's have a look at S upper minus S lower. So S upper is f of x. Oh, actually, you know what? I'll just start it up on the top here. S upper would be f of x0 delta x1 plus f of x1 delta x2, etc. And then minus the lower, which is f of x1. Oh, no, actually, I won't do it that way. That's a little bit messy. I'll do it a bit differently. So, yeah, so actually, do you know what? I'm not going to write all the terms out. Why was I thinking of that? Because it's obvious when you subtract them, what you'll end up with is the sum I equals 1 to n upper, one there minus the lower one there, times delta xi, and that's the sum from 1 to n. And what I'm going to do instead is write this as xi minus delta xi minus f of xi delta xi. Now, as n tends to infinity, we have f of xi minus delta xi minus f of xi tending towards 0 because delta xi is going towards 0 as n goes to infinity. So then that means that this sum here is tending towards 0. So if that's going towards 0 as n is going to infinity, uh, that would mean then that these two are equal in the limit, which is what you need for it to be Riemann integratable. Nope. I don't know. Not too happy with that.